Okay, well, good afternoon. Under the flickering lights here, we're going to take a little thermocouple tour regarding our class. Just to go back a little bit, the thermocouples are formed with two dissimilar metals come together. A small voltage is created, and with thermocouples, that voltage output is dependent on temperature. The types that are common anyway have letter names, type K, type T, type J, and so on like that. And they're made with a couple of different metals. In the United States, we've got a color code. For instance, type K, the yellow insulation designates the positive lead, the red designates the negative. For the next one down, type T, the blue is positive and red is negative, and so on. So we would want one of these tables to use to look things up. I also mentioned that things are different around the world. Depending on where you are, the thermocouple colors are not standardized, at least throughout the world, at least not yet anyway. What do we have here in room 222? We've got tubs. This is a bunch of materials for type J thermocouples. Another one has type E, another material for type T thermocouples. The last one down here is type K thermocouples. This is a thermocouple reader. We can plug in a thermocouple with a common connection. Here's standard connection like this. I'll plug it into the instrument, and the instrument will give me the temperature. And if I put my hands over the thermocouple, that's the wires twisted together here, you'll see the temperature goes up quite quickly. Take my hand off and let the room air take over. Well, the temperature will drop fairly fast as well. So it responds like that. There are a number of connectors. We've got a bunch of them here that can be used with thermocouple readers. We also have some of the old style ones too, but these are the newer style ones. To make a thermocouple, again, we just need to twist a couple of wires together of dissimilar metal, like that, twisted together. They can be soldered, welded. There's other ways to join them, but just something like this works good. The stuff I used to do, we would twist wires together, leave them outside for years in the weather, and they did fine. It didn't matter if we protected them. These ends would need to be connected to the connectors, and we just got to keep the polarity straight, which is plus, which is minus. It's a matter of looking up and getting the color codes. It's fairly straightforward. Some of the wires, some of the brown stuff, it's kind of ugly, but this is high temperature insulation. The yellow, bright yellow stuff is vinyl insulation, so that's not so good for high temperatures. Different probes that we have, and there's more out there. This is a surface temperature probe, so it would be used to measure the surface of something. Thermocouple is that thin piece of metal there. This one here would go into a pipe fitting, has a pipe thread. This type of probe here would go anywhere and could also be used with the ferrule type compression fitting. This one up here is meant to go through, apparently through a bolt, and this is one meant for a high temperature application as well. So those are some samples of what we have. Another type of some interest, these wires, you probably can't see them very well, but they're very thin, and the thermocouple's right at the end, right there. It's very, very small. What the advantage of these is they have a real fast time response. That is a very short time constant. Some students from heavy equipment borrowed some of this stuff. We've got some potting material that they used. They drilled a hole through a cylinder head into the combustion chamber on an engine, and then put these wires down in, put this ceramic potting material in to make a seal, and then they could trace the temperature changes inside an engine as it was running. And that was a good project for them anyway. Not sure what they learned. But a good project. So for type T, we've got a lot of the same materials in there. There doesn't seem to be any high temperature wire, but there's quite a bit of wire. Type E, not so much material. If you like purple, type E might be your thing. Pretty nice color. Type J, there's quite a few. These are high temperature probes. We've got the metal casing on the outside for shielding, and there's a bunch of those. As far as wire goes, there's some of the high temperature wire, the brown wire, as well as the black and blue wires, which are for more lower temperature applications. These are just a little bit of a close-up to what some of those probes look like. This one uses a compression fitting, and this one the thermocouple itself is real small, so it's going to respond quite quick to temperature change if that's needed. This is another one that would use a compression fitting on it. There's a whole bunch of these, and they've been here a long time. Also have the fine wire stuff. So this is largely what we have. Just a couple of requests. One of your predecessors thought he had a problem, so he or she, so they put this silicone sealant on the threads to try to seal it, and don't use that stuff. That makes a royal mess. It hardens up enough that it could be picked off with a knife and scraped forever to try to get it out of there. That clear silicone sealant, just don't use it for anything. I mean, at least anything that's ours, because it messes it up forever. Another student just last year needed some wires, so he took some thermocouple wire and took it out of the casing and used it to hook up electric motor or switches, or I'm not sure what else. But we've got plenty of wire. Just use plain copper wire. Please don't use up the thermocouple wire. That costs a few dollars a foot anyway, depending on the type. We've got spools of it, a limited amount on spools, but just don't use it for anything else but thermocouples. How are we going to get a LabVIEW program to go? And I apologize for the flickering lights here. We'll go up to the beginning here, try to catch on. If you recall with our circuit that we've talked about in class quite recently, this is the basic thermocouple circuit. The junction over on the left at T2 is their unknown, and then we have our leads connected to a meter. The meter is at a temperature T1, which hopefully is known. The math that we did, the output is equal to the EMF at temperature 2, which is an unknown temperature, minus the EMF at temperature 1. We measure the output E sub O with an analog measuring device. Solve that for the EMF at temperature 2, just with some algebra, and then we go to the tables and we find out what the temperature T2 had to be. We can use LabVIEW to do this. Our problem is, how do we establish the reference temperature T1? That is the temperature where we're making our connection to the instrument back here. What you see here is a one way of going about this. This is with the connector boards SC2075, and all I've got the thermocouple connected to is one of the analog inputs right here. I've chosen channel 1 to do that, and get the positive on the positive side, negative on the negative side. The rest of what you see is the circuit for this integrated circuit temperature detector. Let me pull a couple of stray wires out of here. We don't need those. And you did something like this quite a while ago, where we had an integrated circuit temperature detector, except it was packaged like this into a probe form. This is what they look like. I think I remember passing those around. And this is the same circuit that you made, only this time the probe is at the is on the board near where the connections are made. So we would assume that the temperature of the connections here, where the thermocouple is connected, is the same as the sensor's measuring. We can use the temperature we get from this sensor. We can use that as our known temperature, and we can, if we were doing this by hand, we would look up the EMF for that known temperature. However, this is all built into LabVIEW. So the rest of the connections, then we've got the 68-pin cable that goes to an A to D converter, and then that runs through a USB into our computer screen. And I think rather than have you try to watch what I'm doing with all the flicker, I'll see if I can't record the process after this to get this to go with LabVIEW. Okay, to proceed, we need a relationship between our sensor and temperature. And way back when we developed this curve, actually, and maybe we didn't lay it out that way, but you can anyway create for the voltage output coming out of the sensor, what's the temperature? And there's an equation there. It's in the form of y equals mx plus b, only b comes first, and then m, the slope is 100, and e is the x value, or the input value. We'll put that to use in LabVIEW to set up what's called a virtual channel.